The Fourier transform is an equation that takes some function or signal as an input and tells you what amplitudes and frequencies are present in the input. It's always been one of those equations where I knew it worked but didn't really understand it. What do E and I have to do with signal processing? Well, if we're gonna do this properly, we need to start with the definition of E. So imagine we have some function x over time, and this function x increases with respect to its size. In other words, its derivative is equal to itself. This red dot indicates the output of this function. The blue arrow is the point's distance from the origin, and the green arrow, which is always the same size as a blue arrow, shows the velocity of the point, or the derivative of the function. Now, what does a function equal when the input, the time, equals 1? Well, first, let's measure the velocity, but only at the first value when time equals 0, and move at this velocity for 1 unit of time. Clearly, this won't be a very good approximation. Now, let's measure the velocity twice. Once, when the time equals 0, moving at this speed for only half a unit of time. Then we measure again when time equals a half, moving at this new velocity for another half unit of time. Our approximation is getting better, but it's still not very good. Now let's do the same thing, but now we measure 3 times, moving a third of a unit of time at each step. If we continue this process, increasing how many times we measure the function, our approximations get better and better, and in the continuous case, we get exactly what we want, the value of E. Now, in general, we can do this whole process for any time t, and the output will be e to the t. If we scale our input by some constant c, that corresponds to scaling the derivative, the green arrow, by that same constant c. Even though you can get this limit definition from how we defined e, it won't be super important to our discussion, so I won't go over it. Now, let's move up to the complex plane. I want to preface this part by saying that, while the imaginary unit I is usually defined to be the positive square root of -1, in this case it can just be thought of as a number that, when multiplied by, applies a 90-degree counterclockwise rotation. Now, let's do what we just did with the exponential function, but multiply the input by I, which, if you remember, multiplies the green arrow by I, which rotates it by 90 degrees in the counterclockwise direction. This property of our point, its velocity always pointing perpendicular to the arrow from the origin, traces out the unit circle, having radius 1 and being centered at the origin. The fact that our point traces a circle around the origin means that its x-coordinate, or real component, is a cosine of the angle that the line from the center to our point makes with the positive x-axis in radians, and its y-coordinate, or imaginary component, is a sine of the same angle. This formula, e to the ix equals cosine x plus I sine x, will be very important to understanding the Fourier transform. Now we can finally deal with sine waves. Say we have some sine function where the input x is multiplied by some constant, in this case 2. In other words, the frequency is 2. Now imagine that we don't know what this constant is. How would we find it? Well, take some other sine wave with some other frequency. The input is multiplied by some different constant. When we multiply our original wave by this test wave, we get a new function where the height at each input is equal to the product of the heights at each of the original sine waves. If we take the area under this new curve, in other words, take the integral from negative infinity to positive infinity, we get 0. And this can be seen from the fact that every section of the area over the x-axis, the positive area, is counteracted by some other identical part below the x-axis, the negative area. Now let's try this with a different sine wave, keeping the original, but a new testing curve that is much closer to the original. Here the same thing happens, although it's much more subtle. The infinite integral is still 0 for the same reason. Something different happens, however, when our testing curve is identical to the original sine curve. Now all of the area is above the x-axis. In other words, our infinite integral outputs infinity, signifying that we have found our original function. This logic should hold. Multiplying any original function by a bunch of sine curves and getting the infinite integral of the output of that product will tell us how much of those sine curves are present in the original function, whatever it may be. Now, all we have to do is do some symbol pushing to get to the typical Fourier transform representation. But before we go through that, I want to point some interesting things out about this representation. First, the reason we include the cosine is because of phase shift. Basically, if our function is misaligned with the sine function, the cosine curve will make up for it, and the ratios of the outputs of these integrals of the sines and cosines will tell you exactly how much a function is shifted. Secondly, the reason we need to put that imaginary coefficient in front of the integral containing the sine is because we will need to use Euler's formula, which we derived earlier. Third, the reason why we're using x of t instead of y of x or f of x is because this formula is commonly used on signals, and when dealing with signals, it's nice to have it as a function over time, but everything that we've talked about is still applicable. Also, before we continue, that omega is just a wavelength of our testing wave. It's actually a complex number whose real component is a wavelength of the cosine, and the imaginary component is a wavelength of the sine. Now that we got that covered, it's finally time to derive the Fourier transform in its typical form. First of all, let's combine the contents of these two integrals. I know it looks scary right now, but we haven't started simplifying yet. Now we distribute out this x of t from the sine and cosine. This leaves us with cosine of something plus I sine of that something. But hold on a minute. Cosine of something plus I sine of that same something is exactly the form of Euler's formula, so we can transform that into e to the I times that something, omega t. And here we have it, the Fourier transform.